Hello everyone, and welcome to today's chem lesson. Today we are going to be talking about the third type of bonding. We are going to be talking about metallic bonding, which we saved for the very end because it works very differently from the other two types. If we think back to the discussions we've had before, we know that ionic bonding involves a metal and a nonmetal, and covalent bonding involves a nonmetal and another nonmetal, which means the only combination that's left is the one that's here for metallic bonding, is a metal and another metal. The bonding here is not a transfer and it's not sharing, right? So it's not like ionic and it's not like covalent. It's its own separate thing. It's almost a hybrid of both. In a metallic bond, the electrons are all pooled together. All of the metal atoms share their electrons into this universal communistic pool. And this creates a sea of electrons that can kind of just move around wherever it wants. And when we go and we draw this picture in a second, we're going to see that this is the reason why metals can be bent into different shapes, turned into wires, made good conductors. It's all because of this weird sharing of electrons, this weird sea of electrons that occurs when the electrons in metal come together. Let's take a look at a drawing, right? What are we actually talking about here? If we look at a diagram of metallic bonding, we're going to see something that looks like this, where the nuclei of all of the atoms get arranged in these nice even rows and columns. They go every direction, even behind the page and out in front. And this means that if one of these nuclei were to try to move, they get repelled. If this nucleus tries to move to the left, it gets pushed away by this nucleus. If it tries to move to the right, pushed away by this nucleus. Tries to move up, tries to move down, tries to move towards us, out of the page, tries to move back away from us, into the page. No matter which direction this nucleus tries to move, it will get repelled by the other nuclei that are here. So they're locked in place. The electrons get to move around freely between all of the nuclei. They are not stuck in place like a covalent bond. They are not transferred like in an ionic bond. They form this pool, they form this sea of electrons. And they get the ability to just move wherever they are needed, wherever they feel like going, wherever they are pulled to. This is the reason why metals can be magnetic, right? Because these electrons can be manipulated and moved around to make positive and negative ends. This is what allows metals to be great conductors of electricity. This is what allows metals to be bent into different shapes, right? This idea of electron pooling, this sea of electrons. Right, now, Mr. M, why? Why does this make this much of a difference? Let's imagine I have a covalent bond. Two carbons connected together, right? There's more stuff. We're focusing just here. If I swing my atomic hammer down on this carbon, there's no leeway, there's no wiggle room in this bond. If I hit this carbon, this bond breaks. If I swing my atomic hammer down on an ionic bond, and I hit the sodium in this this ionic bond. This bond breaks. I put enough force to separate the positive from the negative. But if I take that atomic hammer and I bring it over here and I hit this nucleus, if I hit this down, it will shift. There's nothing stopping it from moving. It's going to shift its way and shift everything in series down. And I'm going to erase my electrons as I do this. But hitting this nucleus is going to push every nucleus downwards. And it's going to make a dent, as opposed to the others where it just broke. The same thing goes for the reasons why it conducts electricity. Electricity is all about moving electrons. So if these are my electrons, they can take any path they want. They are free to move around. Which means if I need electrons to go from left to right, they can, because there's nothing stopping them from moving. There's no rigid structure for them to stick to. Covalent bonds have a rigid structure. There's no ability for electrons to move around here. Ionic bonds have the same problem. The electrons are stuck. There's no place for them to move around. And so this is what allows metals to be the way they are. This metallic bonding, this sea of electrons. And believe it or not, that's actually it. That's all we've got for today. And I'm going to transition us over to our Zoom meeting for questions, comments, concerns, and attendance. And I will see you there.